Welcome to this scientific investigation of the idea-kill ratio. Today we're going to examine why the world's top inventors and founders systematically eliminate 90 to 99% of their ideas, and why this selectivity is not just beneficial, but mathematically necessary. Let me begin with a paradox. When we study the most successful innovators in history, we find something counterintuitive. Thomas Edison held 1,093 patents, yet only about 10 of them represent major breakthroughs that changed the world. Albert Einstein published over 300 scientific papers, but approximately 7 of them represent truly revolutionary contributions to physics. This raises an important question. Why do prolific creators generate so many ideas if most will be discarded? The answer lies in probability theory. The likelihood that any single idea will be a breakthrough is inherently very low. To find diamonds, you must sift through enormous amounts of rock. Let's build the mathematical foundation for understanding idea selection using expected value theory from decision science. Expected value equals the sum over all outcomes of the probability of outcome I times the value of outcome I. For ideas, this means we multiply the probability that an idea succeeds by the value it generates if it does succeed. Here's where it gets interesting. Idea values don't follow a normal distribution. They follow a power law distribution. This graph shows a power law distribution. Notice how a few ideas at the left have extremely high value, while the vast majority have very low value. This is not a bell curve, it's a dramatically skewed distribution. Mathematically, value is proportional to 1 over x to the power alpha, where alpha is typically between 1.5 and 2 for innovation outcomes. What does this distribution mean in practical terms? It means that the top 1% of ideas typically create 50 to 90% of the total value. The distribution is so extreme that most ideas contribute almost nothing to overall success. Now let's analyze the cost-benefit equation of pursuing ideas. Every idea you pursue has costs. Cost equals T times R plus O, where T is time invested, R is your hourly rate or opportunity cost, and O represents other resources, like money or team effort. Research shows that the average idea pursuit requires 40 to 200 hours of focused work to properly evaluate. For a founder with an opportunity cost of $200 per hour, this represents $8,000 to $40,000 per idea pursued. This brings us to the core problem. How do we design filters that identify high-value ideas before we invest significant resources? We can measure filter quality using 2 metrics: true positive rate, the percentage of good ideas we correctly identify, and false positive rate, the percentage of bad ideas we incorrectly pursue. This is called an ROC curve. The red diagonal line represents random guessing, which is useless. The green curve represents a good filter, which correctly identifies most valuable ideas while rejecting most poor ones. The yellow dot shows an optimal operating point. Unfortunately, human psychology introduces systematic biases that sabotage our natural idea filters. Let's examine the key cognitive biases. First is the sunk cost fallacy. Once we invest time in an idea, we irrationally continue investing even when evidence shows it won't work. Second is confirmation bias. We selectively notice evidence that supports our idea while ignoring contradictory evidence. Third is the endowment effect. We overvalue ideas simply because they're ours, similar to how we overvalue possessions we own. Fourth is optimism bias. We systematically overestimate the probability of success, with studies showing founders typically estimate twice the actual success rate. Mathematically, perceived probability typically equals 2 times actual probability for entrepreneurs evaluating their own ideas. How much do these cognitive biases actually cost us in wasted effort? Research shows that 60 to 80% of ideas that get pursued fail early validation tests. Most of these failures could have been predicted with better filters. Now let's derive why a 90 to 99% kill ratio is mathematically optimal. The number of ideas you generate times the probability an idea is good, times 1 minus the probability you miss it with your filter, must be greater than or equal to your target number of breakthroughs. Let's plug in typical parameters observed in studies of top innovators. The base rate probability that a random idea is actually good ranges from 1 to 5%. Even with good filters, you'll miss 10 to 30% of good ideas due to early-stage uncertainty. To reliably find one breakthrough, you need to generate 50 to 200 ideas and filter aggressively. This graph shows the probability of finding at least one breakthrough as a function of ideas generated. Notice that to reach 90% confidence, you need to generate approximately 115 ideas, which means killing about 114 of them. Now let's design a practical framework for effective idea filtering based on decision theory. Stage 1 is a rapid initial filter, taking 5 to 15 minutes per idea. This eliminates 70 to 85% of ideas. Ask 3 key questions. Is the problem large enough to matter? Does a real market exist? Is it technically feasible with current technology? Stage 2 is deep analysis, taking 2 to 8 hours. This eliminates another 10 to 15%. This stage includes competitor analysis, customer discovery interviews, and preliminary financial modeling. Stage 3 is prototyping, taking 1 to 4 weeks. This is where you build a minimum viable prototype. Only 2 to 5% of original ideas should reach the prototype stage. This is where significant resources get committed. This funnel diagram shows the filtering cascade. You start with 1,000 ideas. After rapid filtering, 150 proceed to stage 2. After deep analysis, 20 proceed to prototyping. Finally, only 1 to 2 actually launch. This is a 99.8% kill ratio. At this point, you might ask, isn't this incredibly wasteful? What about all those killed ideas? The answer is that killing ideas early is dramatically more efficient than pursuing bad ideas far into development. Cost to kill an idea early is perhaps 15 minutes times $200 per hour, which equals $50. Cost to kill an idea late, after building it fully, is 500 hours times $200, which equals $100,000. Early killing is 2,000 times more efficient than late killing. This is why aggressive filtering is not wasteful, it's essential. Effective filtering requires rapid feedback loops. Let's examine how to structure these. Feedback loop speed is a critical performance metric. How quickly can you test an idea and get real data? Cycle time equals design time plus build time plus test time. Studies show that top innovators reduce their cycle time by 10 to 100 times compared to average practitioners. This graph compares fast versus slow iteration cycles. The green line shows someone testing 2 ideas per week. The red line shows someone testing 1 idea every 5 weeks. After 1 year, the fast iterator has tested 100 ideas while the slow iterator has tested only 10. This 10 times difference is transformative. Let's quantify how to measure and improve filter effectiveness using metrics from machine learning. Precision equals true positives divided by true positives plus false positives. This measures what fraction of ideas you pursue that actually succeed. Recall equals true positives divided by true positives plus false negatives. This measures what fraction of good ideas you successfully identify. For effective idea filters, we want specific target metrics. Precision should be greater than 40% at stage 2, meaning at least 40% of ideas entering deep analysis should be viable. Recall should be greater than 70% overall, meaning you catch at least 70% of truly good ideas. Let's examine common ways that idea filters fail and how to avoid them. Failure mode 1 is overfiltering, where you kill too many good ideas because your criteria are too strict or too conventional. Failure mode 2 is underfiltering, where you pursue too many bad ideas because you're not selective enough or too optimistic. Failure mode 3 is using wrong criteria, where you optimize for easily measurable but ultimately unimportant metrics. This table shows 3 filtering regimes. Overfiltering has high precision of 80% but low recall of 30%, causing you to miss opportunities. Underfiltering has very low precision of 15% but high recall of 95%, causing you to waste resources. Optimal filtering balances these at 45% precision and 75% recall. Idea filtering connects to a fundamental problem in decision theory called the exploration-exploitation trade-off. Exploration means testing new, uncertain ideas where you don't yet know the value. Exploitation means doubling down on ideas that you've already validated as winners. The optimal strategy maximizes the sum of expected value from exploration plus expected value from exploitation. In your early career, you should bias heavily toward exploration, perhaps 90% of effort on exploring new ideas. Later in your career, after you found winning patterns, shift toward exploitation, perhaps 70% on proven approaches. How do highly successful innovators actually implement aggressive idea filtering in practice? They use systematic, documented processes rather than relying on intuition alone. Thomas Edison created what he called an invention factory. He had explicit, documented criteria for which inventions to pursue. Edison's three main criteria were commercial potential, manufacturability at scale, and intellectual property protection. Ideas had to score highly on all three. Let me give you a practical framework you can implement immediately. Step 1. Write down your filter criteria explicitly. Don't rely on gut feel. Create a scoring rubric. Step 2. Keep a log of ideas you pursued that failed and ideas you rejected that succeeded. This gives you data to improve your filter. Step 3. Set explicit target kill ratios. For example, Stage 1 should eliminate 80%. Stage 2 should eliminate another 70% of what remains. Step 4. Use forcing functions like time limits or required peer review to maintain filtering discipline. These 4 components form a complete system. The scoring rubric provides objective criteria. Historical data improves calibration over time. Kill ratio targets create accountability. Forcing functions maintain discipline when you're tempted to skip filtering. Let's examine the long-term compound effect of improving your idea filter quality. Total value created equals number of ideas pursued, times average value per idea, times probability of success. Improving your filter from mediocre to excellent increases average value per idea by 3 to 10 times because you pursue much better ideas. This graph shows cumulative value over 10 years. The red line shows linear growth with poor filtering. The green line shows exponential growth with good filtering. By year 10, good filtering produces 3 times more total value. This difference compounds over your entire career. For those interested in advanced techniques, let's discuss Bayesian updating of idea quality estimates. The probability of hypothesis H given evidence E equals the probability of evidence E given hypothesis H times prior probability of H divided by probability of E. This is Bayes' theorem. You start with a prior probability based on historical base rates for similar ideas in this domain. As you gather evidence through customer interviews, prototypes, or market tests, you update your probability estimate. New probability equals old probability times the likelihood ratio of observing this evidence if the idea is good versus observing it regardless. Let's address the psychological difficulty of killing your own ideas. This is where many people fail. Loss aversion makes killing an idea feel twice as painful as the equivalent gain from pursuing a better idea feels good. We often attach our identity to our ideas, making rejection of an idea feel like rejection of ourselves. A key strategy is to temporarily separate idea generation from evaluation. Generate ideas in one session, evaluate them in a later session when you're more objective. Another strategy is to involve external reviewers who don't have the same emotional attachment to your ideas. Top innovators often think in terms of portfolio theory from finance, applied to ideas. Just like financial portfolios, you want diversification. Don't put all your resources into a single idea. Balance your portfolio between safe, incremental ideas and high-risk, high-reward, moonshot ideas. A common allocation is 70% in safer proven ideas and 30% in moonshot ideas with huge potential but low probability. This raises a critical question. When should you persist with an idea despite setbacks versus when should you kill it? The answer is to use pre-specified decision criteria rather than emotion or stubbornness. Before you begin pursuing an idea, write down specific kill criteria. For example, if we can't find 10 customers willing to pay after 3 months, we stop. Similarly, set pivot criteria. If we discover market segment A doesn't want this but segment B does, we pivot. This table shows example decision criteria. If customer interest is below 10 paying customers, kill the idea. If unit economics show negative margin, pivot the business model. If market size is below $10 million, kill it. These are specified in advance, not decided emotionally in the moment. The most successful innovators engage in meta-learning, where they deliberately improve their filtering process over time. Track your prediction accuracy. Of the ideas you decided to pursue, what percentage actually succeeded? Also track missed opportunities. Are there ideas you rejected that someone else successfully executed? Your learning rate is proportional to 1 over the square root of number of attempts. This means early in your career you learn quickly, but you need many attempts to continue improving. Let's look at empirical results from academic research on innovation success rates. Research shows that only 10 to 20% of startups achieve true product-market fit. For new products launched by existing companies, 25 to 40% meet their revenue targets. Of all patents filed, only 5 to 10% ever generate positive return on investment. This graph shows actual versus theoretical performance. The red dashed line shows perfect prediction, where every pursued idea succeeds. The green line shows actual 15% success rate. The gap between these lines represents the enormous value of better filtering. Let's quantify the economic impact of improving your idea-kill ratio. Value created from better filtering equals time saved by not pursuing bad ideas, times your hourly rate, plus the additional value from pursuing better ideas instead. Consider an entrepreneur with 40 hours per week for 1 year, so 2,000 hours total. Scenario A with poor filtering. They pursue 20 ideas. Each takes 100 hours. 5% succeed, so 1 success. Scenario B with good filtering. They pursue only 5 ideas, but each is much better. Each takes 400 hours. 40% succeed, so 2 successes. The impact is 2 times as many successes with the exact same time investment. This is the power of better filtering. Let me synthesize everything into a complete mental model you can use. First principle. Ideas follow a power law distribution where most have near zero value and a few have enormous value. Second principle. Cognitive biases systematically make us over-pursue mediocre ideas and under-filter. Third principle. The optimal kill ratio is 90 to 99%. Not because we're wasteful, but because this maximizes long-term value creation. Fourth principle. Systematic, documented filters consistently beat pure intuition at scale. Fifth principle. Deliberate meta-learning allows you to continuously improve your filter quality over your career. In conclusion, knowing these principles is not enough. Implementation matters more than knowledge. Most people intellectually know they should be more selective with ideas, but very few actually implement systematic filters with documented criteria and tracked metrics. The winners are not necessarily smarter or more creative. They are the ones who actually implement aggressive, systematic filtering. Your action item this week: design your own multi-stage filter system with explicit criteria and target kill ratios for each stage.